Welcome everyone. In this video I will show you how to read the performance chart of the Peltier coolers and how to apply them on a real-life example. So I got an example in one of the comments, in the comment section of one of my videos, and I thought that that's quite fun to discuss and quite interesting. So I would like to use that example in this video to show you how to understand this chart, which you can see on the left side of the screen. So let's go to the example. So that example was the following. So there is an enclosure, and I try to draw it down nicely. So enclosure, this is a box, and it contains some electronics. So we have a closed box, and it's separated from the environment, and we have a few other electronics inside, and they generate the heat, of course. So what happens is that the temperature inside the box goes up, and since it's a closed system, so there will be a final temperature which is determined by the heat transfer between the walls of this box and the environment which surrounds this thing. And let me write down a few details. So what we know, or what we assume, that the temperature inside is roughly 70 degrees or 80 degrees Celsius. For the sake of simplicity, I will use 70 degrees. We also know the power consumption or the power usage of the electric devices inside the enclosure, and I just use a P here with that, and the total power consumption of the different devices was around 112 watts. So what we have here is a very good, or I hope it's good, overestimation of the total heat rejected by these units, because of course they use the electricity, but they don't convert 100% of this 112 watts into heat. But if we assume that they convert all this power that they take from the electric outlet into heat, then we overestimate the generated heat, and that's good for us, because our formula will be more, or our calculations will be more closer to the reality, hopefully. So what this person did, or tries to do, is that there is, let's say, a hole on the top, not a perfect hole, but now I try to idealize and improve his thing. So there is a hole on the top of this thing, and in that hole, let me just write it, or let me just draw it here. So in that hole there is a Peltier cooler, and I try to draw in a separate units. So this is the hot side, and this is the cold side of the Peltier cooler. So the cold side is in contact with a heat sink, and the hot side is connected to a CPU cooler, and this is a 12706 unit. And what happens inside is that there is a fan, and that fan circulates the air. So the only heat transfer between these two units, so between the heat sink and the devices which generate the heat, is happening through the air. So what happens if we try to make a diagram is that we have our device here, and the heat exits them and getting transferred through the air to the cold side heat sink, so CH, let's say. And then from the cold side heat sink, the heat goes to the cold side of the Peltier cooler, so let's say CP. And then as you run the Peltier cooler, you transfer the heat from the cold side to the hot side. So that will be the HP, like the hot side of the Peltier unit. But here you cannot stop, because you have to remove the heat from this, otherwise everything will just overheat. So let's say that now we have our CPU cooler here. So that's how the heat travels in a very simplified way. So what we have to do here is that we have to make sure, first of all, that there is a good contact between the devices and the cold side heatsink. So we have to make sure that the fan which provides the circulation inside the enclosure provides a very good circulation. So what I would do here is I would put the fan directly on the heatsink, blowing in this direction, and that would, like, let's say, pick up the air from the inside and then push the air against the heatsink, so that heatsink would be experiencing a lot of warm air. So that warm air, of course, would transfer the heat to the heatsink, and then we could pump it out. So that could be one thing that should be considered. But now in our simplified case, we just assume that everything is in perfect contact. So basically we just simplified this part into one block in order to make it more easier for us to think about this thing. So what we know is the inside temperature. So that was, let's say, 70 degrees. We know that the power taken by these units, total power, is 112 watts. We also know that the ambient temperature, so outside the box, can be 33 degrees Celsius. And basically that's all we know. And if I remember correctly, we also knew that we are using a 12-volt power supply. I don't know the current, so that's a missing thing. But I assume that it is capable of providing 6 amperes, so we can run this thing on the maximum power. So now, as I described the problem here, let's go to the performance chart and let's think about what we can do. So this performance chart is defined at 50 degrees hot side temperature, which means that if you can maintain the temperature of this part here perfectly at 50 degrees Celsius, you should get these numbers that you can see here with these different linear functions. So we assume that that's actually a good assumption, that we have like 17 degrees difference here. So this is some delta here. So that means that if our CPU cooler is very good, then we might be able to maintain the 50 degrees Celsius on the hot side. So first of all, this is one of the assumptions that we apply. Apart from this, that we constantly maintain 50 degrees on the hot side. And then what we want is to see what we can do on our performance chart. So in an idealized case, we don't really want to have temperature difference between the hot side and the cold side, because if you see, the enclosure temperature is much higher than the temperature outside the enclosure. So let me just, so here we have 70 degrees, and let's say here we have 30 degrees, just to make it a bit more easier to see numbers. So 40 degrees difference. And we know that with these certain settings that we can read from the performance charts, we can maintain 50 degrees Celsius. So let's say that we are aiming for 50 degrees Celsius in the inside. So that means that actually we can maximize the heat transfer or cooling, or maximize the pumping of the heat based on these numbers. So let me write it down again. So the ambient temperature is 30 degrees. And then the hot side temperature is 50 degrees, and the enclosure temperature is 70 degrees. So we know that between these two we have 20 degrees Celsius difference, but this doesn't matter. And also we know that here we have 20 degrees Celsius. I just write this down to see the numbers in a better way. So what we can do here is, since the temperature that we want to reach is inside this box is still higher than the ambient temperature, we can use the highest possible Q. So what that means in our case is that we could simply say that the DT is 0 degrees Celsius. So now we go to the performance chart and we write down that the DT is 0 degrees Celsius. So that will mean that the cold side will be also 50 degrees Celsius. So the heat sink will be at 50 degrees. And then we have to draw a vertical line at DT equals 0. And then we have to read the different numbers. So first of all, let's say that we can provide 12 volts. So that this is one of our limiting factors. So at 12 volts, I have to draw a horizontal line. But it really doesn't make sense because we are at DT equals 0. So we have to see what is the current here. So what you have to see is that this line here is 6.1 amps and this line here is 5 amps, and this is roughly halfway between those two lines. So this is 5.5 amps, let's say. So now we know that if we have DT equals 0 and U equals 12 volts, then the current will be 5.5 amps. And from this, we can calculate the power. So basically just the product of this. And this is 66 watts. So this is one part of the rejected heat which appears on the hot side of the Peltier cooler and has to be removed by the CPU cooler. But we don't stop here. So now we know what kind of voltage and current values we have here. We know the DT. So we go up to the other side of the performance chart, which is still DT on the x-axis, but QC, so the cooling power, so the heat which can be pumped by the Peltier cooler on the y-axis. So we were at 5.5 amperes from here. So we try to look for the same. So again, we try to aim in between these two curves, so roughly here. And then we see that we have these two major ticks here, 60, 75, and the minor ticks is 4 here, so we have 5 divisions. So this difference is 15, and you have to divide 15 by 5, so each minor tick is 3. So this here is 63. So now we can write down that the QC is 63 watts. So we have to summarize this. So P plus QC, and let's say that this is 130. So just a little bit of rounding up. So 130 watts will appear on the CPU cooler if you are providing 12 volts, 5.5 amperes, and the hot side is maintained at 50 degrees and the cold side is also at 50 degrees Celsius. And this is just one unit, and you can see that by 1 unit you can remove 63 watts. And if you remember, the P was defined as 112 watts. So if you can run the device like this, you can be halfway in the process, let's say. So if we take the P, the original P, then let's divide the P by the QC, and let's say that is roughly 2. Of course, it's a bit less, but still. So this is roughly 2. So this says that we need 2 units. But you need 2 units, and you need a very good CPU cooler, because this is 130 watts. Just to give you some perspective, nowadays the top desktop CPUs are generating roughly 95, 105 watts. Most of these Intel or AMD processors. So the CPU coolers for them are also sized for this sort of performance. And you have to look for some high-end cooler in order to be able to remove that heat, so 130 watts. So this was our example, one part of it. So once again, I just want to go through the details from the beginning. So the problem was, we have an enclosure which has higher temperature than the environment's temperature. So inside we have 70 degrees and outside we have 30 degrees roughly. And what we want is we want to decrease the temperature inside this enclosure. And we can take the performance chart and our details in order to estimate the numbers. So we know the temperature values, and we know that the devices inside generate roughly 112 watts heat. We know that the power supply that we use for the TEC12706 is a 12 volt power supply. I don't know the current, but I assume that it can provide a lot of current. So we are limiting the current with the 12 volt and also with the certain choices with the DT. But what we say that we can maintain the temperature of the hot side at 50 degrees Celsius, and actually we want to reach the same temperature inside the enclosure. So we want to decrease the temperature here by 20 degrees. So we end up having 50 degrees inside. And by that, we say that in this case, the DT will be 0. So the temperature difference between the hot side and the cold side. And if the temperature difference is 0, so DT is 0, we have to read the performance chart that, okay, if we have DT equals 0 and we can provide 12 volts, what is the current that we can run through the device? So then we see that, okay, we can run 5.5 amps. We can go up then to the other side of the, or other part of the performance chart, which is DT versus QC. And now we see that, okay, we have 5.5 amperes available. What is the QC that we can reach at 0 degrees DT? So we are still along the y-axis, and we search for the 5.5 ampere, that is roughly here, and we read the QC, which is 63 watts. So that means that with the previously mentioned parameters, with 1 unit we can provide 63 watts of cooling power. And that is roughly half of the heat that is generated inside the box. So we are almost there. So if we have 2 of these units, and we assume that the thermal contact between the enclosure, between the devices inside the enclosure and the heat sink attached to the cold side of this unit is good, then by 2 units we should be able to maintain 50 degrees inside the enclosure if these devices are constantly generating less than 112 watts. But this is of course some rough estimation, but I think that this is quite close to the reality. But we also have to make sure that we cool the hot side quite nicely, because by 1 unit we generate 130 watts, which consists of 2 terms. One term is coming from the rejected heat based by just the joule heating of the unit. So if you run this unit at 5.5 amps and it takes 12 volts to reach the 5.5 amps, then the heat will be 66 watts, and that appears on the hot side. And of course you are also moving heat from the inside of the enclosure through the Peltier unit to the CPU cooler, and that is another 63 watts. So the sum of these 2 terms will give us 130 watts in total. So that appears on the CPU cooler, or more precisely on the hot side of the Peltier cooler, and that has to be removed by the CPU cooler. So here in this part you will need a very efficient cooler, a good CPU cooler with a high throughput fan. So this was the real-life example demonstration of the performance charts, but before ending this video I want to show you another example which can be interesting for you. So let's jump to a clear chart now. So let's see what is the role of the different current values or different DT values. So for example, let's say that we want to run our device at 14 volts. So we have 14 volts power supply. So let's draw a horizontal line here at 14 volts. And you see that this horizontal line intersects two curves which correspond to two different currents. So let's draw a vertical line at the first intersection, so roughly here. And let's see what happens here. So this corresponds to 6.1 amps that we know. And if we check the DT, then the DT1, let's call it DT1, is roughly 18 degrees Celsius. So what we see here immediately, let me write this down. So DT1 is 18 degrees Celsius. So this is the difference between the hot side and the cold side. So in ideal case now, the cold side is TH minus 18, which means that 50 degrees minus 18 degrees, so 32 degrees. So with this case, we can maintain 32 degrees Celsius on the cold side. And we also know that we are at 14 volts and 6.1 amps. So that will bring us the rejected heat or the generated heat at around 85.4 watts. And we can check the QC as well. So we drew this very long vertical line and 6.1 amps. So we go here and draw a horizontal line again. So we see what happens here. And the QC is roughly 51 watts. So we can summarize these two. So P plus Q is 131.4 watts. So this appears on the hot side of the Peltier cooler, and this has to be removed by a cooler attached to the hot side. But we see another intersection here, and let's see what is here. So I again drew a very long vertical line. So here we are at 5 amps, and DT2 now is 63 degrees Celsius. So let me write it down. So this is 63 degrees Celsius. The U is still 14, but the I, so the current, is just 5. And here, the cold side is minus 13 degrees. So you see that we can reach much colder cold side, but at what cost? So first of all, let's see. The P, of course, will be smaller because the current is lower a bit. So here, this is just 70 watts, so 15 watts lower. But let's read the QC, and now you will be surprised. So we go to the sine curve here, and now you see that this is just 12 watts. So first of all, let's summarize this. So P plus Q, and this is just 82 watts. So P plus Q equals 82 watts, as you can see. So this is much lower, 50 watts lower than the previous. And most of this 50 watts comes from the difference between the cooling power. So the cooling power differs by 39 watts. So 39 watts, and that's a huge amount. So what you can see here in the demonstration is that exactly the thing that I always try to emphasize in my videos or in my comments. So a lot of people are confusing the things that if you have a very low temperature, so the delta T is high, if you have a very low temperature on the cold side, then it's a so good cooler, so you could use it as an air conditioner or something. But the main principle of cooling is that you want to transfer heat. and by transferring the heat, so for example removing the heat from material A and putting somewhere else, that's how you decrease the temperature of the object. So the exact same principle happens here. The reason why they can measure, or I also can measure, very low temperatures on the cold side is because there are no objects attached to the cold side of the Peltier cooler, which means that the Peltier cooler doesn't have to transfer too much heat from anywhere, because A, there is no things attached to it, or there are no heat sources. B, the contact between the surrounding air and the cold side of the Peltier cooler, even when it is exposed, is not that good. So there will be no significant heat transfer, and this small heat that can be transferred from the cold to the hot side is just enough to balance out that thing. So these two things are really influencing this stuff. So when you see that someone shows a very low temperature on the cold side of the Peltier cooler, that means that they cannot cool with it, because all the cooling power which appears on the cold side, because there is still cooling power but very small, but all that cooling power is invested in cooling the very small environment of the cold side. So what you can see here is that if you have a high dT value, then you have a very low QC value. And if you cannot have high QC, that means that you cannot transfer heat. And if you cannot transfer heat, then you cannot cool. So if you would try to do the same by having some large object on your cold side of the Peltier cooler, then you would see that it would take so much time to reach the same thing here, because at a certain unit of time you can just transfer 12 watts instead of 51 watts. So this is, let's say, a factor of 4 in between the two cooling power differences. So you can see that yeah, if you have high dT values, so you are in this part of the curve, then if you check the performance chart, then you will be around the bottom. And the other way around, so let's say we have low dT, so the temperature difference between the two sides of the Peltier cooler is low, so you are somewhere here, you can reach quite meaningful numbers. So you can see that that is high QC. So here, actually here where you should cheat, or not cheat, but use the physics. So if you know that you will want high QC, then that will require low dT. And how can you make a low dT? Well, you have to maintain already cold temperatures on the hot side. So that means that if you want to use this kind of approach, so you want to cool something, you already have to have very cold hot side. So for example, if you want to reach, let's base our discussion on this chart. So if you want to reach 0 degrees Celsius and you want to have a reasonable QC, then you have to maintain your hot side at 20 degrees Celsius. Of course, this chart is valid for the 50 degrees hot side, but I just want to use this simply. So we want to reach 0 degrees, and the hot side is constantly maintained at 20 degrees Celsius. So we go for dT equals 20. And we run the maximum current, so 6.1 amps. So we are here. So you see that we are able to move almost 50 watts of power from the cold side to the hot side. But and we can reach 0 degrees, but that means that we have to keep our hot side relatively cold. So that's very difficult. So once again, you have to pick one of these. either you reach high temperature differences between the two sides, but you cannot cool anything properly, or it will need very long time, or you sacrifice from the temperature difference or cool your hot side by some other methods, let's say below ambient temperature, and then you can transfer reasonable amounts of heat. But this thing becomes more and more difficult if you want to pump out more heat, because let's say if you start at the bottom of this chart and you want to have this 20 degrees difference, so here if you want to have, let's say, 5 watts, then you just need 1 amperes for that. So your P will be very low. So that is, I don't know, 3 point something. So let's say the P here is 4 watts, let's say. So here you put a very low amount of power on, or heat, sorry, on the hot side. So this is fine. You don't really have to struggle with the cooling of the hot side. But as you move up, so here we are at 2 amps, and here the P at 2 amps is now, if you see this line is let's say 10 watts. So then the rejected heat on the other side will be twice as much as previously. And then if we move to 3 amps, so we are here, yeah, we can almost cool with 30 watts of cooling power. But if we check here, then this is let's say 7.5 watts. So now the P is roughly 22 watts. So more and more heat is appearing on the hot side. So your cooling has to be more and more efficient. So this is the drawback. So then, of course, the DT becomes more and more difficult to maintain. So let me try to draw this. So here you want to have a QC, and here you have to have a DT. And this is not the same chart as here. This is just some arbitrary chart. So as you try to increase the DT at a certain QC, you will see that you have to cross different currents. So you have to increase the current. But as you increase the current, then the P, the rejected heat, let's say, or let's call it rejected heat, that also increases. So that's really difficult. So here you can see that, for example, if I draw a line of a linear line at 45 watts, so you can see that with 1, 2, 3 amps you cannot even reach that high cooling power. So you have to go more than 3 point something watts. So here you can have some DT which is let's say 13 degrees, but you need 4 amps for that. So if you want to increase the DT at the same cooling power, so you want to reach lower temperatures while being able to maintain the same cooling power, then you have to give more current to this device, and then you are like maximized here. So 27, let's say, or 26 DT at 6.1 amps. But then at 6.1 amps you will have an enormous amount of rejected heat. So then, in order to be able to maintain the same DT with the same QC with increasing DT, you always have to have better cooling on the hot side. And actually now I have some more tools to demonstrate this to you. So in the next part of this video I will actually show you this thing with the charts and with the units. So I think I finished this video here because it's quite long now, but I still hope that it worth the effort and I could help you somehow. And I hope that you learned something, and now you can read and understand the charts, and most importantly you can accept the fact that you cannot really cool with the Peltier units as efficiently as with other types of coolers. So for example, the compressor based coolers. So it's just, you can immediately see on the charts, and you cannot change the charts because these are their physical properties or physical performances. So you cannot really do anything else that is limited by the charts shown on the picture. So please try to understand that if you want to have a good cooling performance, you will need a lot of power, and you will need a very good cooling of the hot side, because all the power that you pump into the Peltier cooler will be appearing on the hot side of the Peltier cooler. And if you don't remove that, then the Peltier cooler will not work, because you have to maintain the certain differences between the two sides to, let's say, obey these curves defined by the manufacturer. So you can see that either you have high temperature differences but you cannot cool anything, or it would take enormous amount of time to reach that low temperature because of the low cooling performance, or you can have good cooling performance but you cannot reach very low temperatures, and you always have to start from the hot side. So if you cannot provide good cooling on the hot side, you cannot even think about reaching reasonably low temperatures on the cold side, because you cannot really dump the heat from the hot side anywhere if you have bad cooling. So the heat, let's say, this is not as easy as I explain it, but the heat just accumulates on the hot side, and after a certain time you just cannot accumulate more heat because you are limited by the cooling, and the performance of the device just decreases. If I really want to simplify, but it's not this easy, but something like this happens. So yeah, I think I end it here, and I hope you liked this video. Please consider subscribing my channel, so I will put out more of these details and more of these explanations, and see you in the next video.